Imagine trying to keep a secret message perfectly safe in a world full of noise and disturbances. In the realm of quantum computing, our precious quantum information faces an even tougher challenge. Physical qubits, the tiny building blocks of quantum computers, are incredibly fragile, constantly battling against errors caused by environmental interactions. So, how do we protect them and ensure our quantum calculations remain as accurate? Logical qubits encode physical quantum states by distributing quantum information across multiple physical qubits, effectively creating a more robust, error-resistant quantum unit. This clever technique, known as quantum error correction, allows us to detect and even correct errors without directly measuring and disturbing the delicate quantum state itself. The core mechanism behind this is redundancy and entanglement. Instead of storing one bit of information on one physical qubit, we use several. For instance, a simple error correction code might use 3 physical qubits to representing one logical qubit. If one of these physical qubits experiences an error, like flipping its state from 0 to 1 when it should have remained 0, the other 2 qubits still hold the correct information. The magic is that this isn't just classical redundancy. The physical qubits are entangled, meaning their fates are intertwined. This entanglement allows us to perform syndrome measurements, which are indirect measurements that tell us where an error occurred without revealing the actual quantum state, thus preserving its coherence. Practically speaking, encoding quantum states involves several steps. First, we prepare a set of physical qubits in a specific entangled state that represents our desired logical 0 or logical 1. This preparation uses quantum gates, much like building a tiny quantum circuit. For example, in a 3 physical qubit code, a logical 0 might be encoded as the entangled state where all 3 physical qubits are 0. A logical 1 would similarly be an entangled state where all 3 are 1. Next, throughout the computation, we repeatedly apply syndrome measurement circuits. These circuits interact with the physical qubits and output classical bits, which indicate if and where an error has occurred. Finally, based on these classical syndrome measurements, we apply corrective quantum operations, such as a bit flip or a phase flip gate, to restore the faulty physical qubit to its correct state, thereby preserving the logical qubit's integrity. This process is incredibly complex, involving sophisticated quantum error correction codes like the surface code, which is a leading candidate for fault-tolerant quantum computing. The surface code, for instance, might requiring hundreds or even thousands of physical qubits to reliably encode just one logical qubit. This overhead is a critical challenge in scaling quantum computers, but it is also what unlocks the path to truly powerful, fault-tolerant systems. Without such encoding, the inherent fragility of physical qubits would make any large-scale quantum computation impossible, as errors would accumulate too quickly, corrupting all results. Ultimately, logical qubits serve as a protective shield for quantum information, transforming inherently noisy and error-prone physical systems into reliable computational units. By cleverly distributing and redundantly encoding quantum states across multiple entangled physical qubits, and then continuously monitoring for errors without disturbing the quantum information, we can build the robust foundations necessary for future quantum computers to tackle problems currently beyond our reach, moving us closer to realizing the full potential of quantum advantage.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.